All right, so today for our seminar, we have Sebastian Kozuch. Just to give a very short introduction, he's originally from Argentina, did PhD in Israel in the Hebrew University. After the PhD in 2009, and from 2009 to 2012, he postdoc in the same country, Weizmann Institute of Science, 3 years postdoc, and after that, becoming a research scientist. He went to the US research scientist at the University of North Texas. That is where he and I had overlap about 1 year or something like that. Afterwards, he got a permanent, independent position in the university, in the Ben Gurion University of the Negev, where he now became an associate professor. Okay. So Sebastian works in catalysis, chemical bonding, and heavy atom tunneling. So we are actually very lucky to have him here today, because last week he was attending the international workshop on quantum atomic molecular tunneling systems. He gave a talk there, and it was very nice. So today we'll hear something very similar. And with that, please.
Thank you. Okay, well, yeah, it's a real pleasure to be here. I mean, I haven't seen Bo for like 10 years since we departed from Texas, so coming here again to work with him. I have to stand here so the Zoom can...
It's okay.
Okay?
Yeah, I guess.
Yeah, here. Yeah, I'm one with the people. Okay, so you will hear today a lot of heavy atom tunneling, right? Now you know that quantum tunneling, most of you are physicists, or no, not really. Most of you are chemists. Who is a physicist? Raise your hand. 1, 2, 3. That's it. Chemist. Biology.
You're in trouble.
Okay, so this is a talk for chemists. Great. So let's start. Hopefully. In a second. There we go. So my group, it's a small group. Yeah, I work with a small number of people. So we divide our work in 3 main fields: the chemical bond, halogen bonding, and non-covalent interaction mostly, but not only. Lots of catalysis and kinetics with mostly the energy span model. If you heard about it, please tell me that you heard about it. Nobody, we need to talk.
I know.
Yeah.
Yeah. It was very well known, I have to say. Well cited, right? The paper.
He's a very good friend. And quantum tunneling, of course, what we are going to talk today in 2 parts. One is exothermic reactions, and the second is isothermic reaction. Okay, so everything starts with this equation for the physicist. You can start sleeping now, you know this stuff. The de Broglie wavelength gives us a kind of guide of how much dispersed a particle is. Yeah, we are meaning here mostly atoms, right? But not necessarily only atoms. So, for instance, if we have an electron whose mass is really, really small, with a certain amount of energy, that it's logical amount of energy, we can say that the electron can fly around 45 angstroms. Okay, it can be moving, it can be dispersed through that distance. This is like a hummingbird flying from place to place. You will understand why the hummingbird. If you have hydrogen with much bigger mass, it can move it's dispersed for around 1 angstrom. Just to have an idea of this will mean that approximately, in a very rough number, if it can tunnel, it will tunnel to a distance of around 1 angstrom, not much more than that. So If the electron is a hummingbird, the hydrogen will be like a vulture. Yeah. They are much heavier. They don't like to fly too much. Actually, I did the math. The difference in math is pretty similar. Yeah. So a vulture, now you know, a vulture weighs something like 2,000 hummingbirds. But if you have carbon, the mass of carbon, obviously, it's much bigger. Now, the distance depends on the square root of the mass. So the distance will not be 12 times shorter, but more or less 1/4, 1/3 of the distance. So it will be dispersed for around 0.3 angstrom, and that's a distance that it will probably tunnel, which is a very, very, very short distance for a chemical reaction. That's not very common. So this will be like, really, I did the math. Yeah. So tell me, when was the last time you saw an ostrich flying? Okay, so today, this lecture will be about flying ostriches. So if you have a thermal reaction, right? Classical reaction. What is a classical reaction? You have lots of particles moving randomly in the reactant wall. And then from time to time, one particle will have enough energy and direction to cross the barrier, right? The probability of doing this is, according to Arrhenius, according to Eating and many others, let's say exponential with minus exponential with the activation energy, right? This is classical chemistry. But if we have quantum tunneling, you have a particle in the reactant part of the profile. Something mysterious happens in the middle who nobody understands it, and it goes to the other side. Yep. Okay. This depends on the square root of the mass. Remember the Broglie wavelength. On the square root of the activation energy. But the most important factor of all is the distance that it is tunneling. Okay, so you see the distance is outside any square root. So from all the measures that you have there, the distance is the more critical. If the reaction is narrow enough, then it has a chance of tunneling. Okay, even if the barrier is not so high, but significant. Okay, there are tons of examples of heavy atom tunneling with carbon. Most of them are with carbon, but there are some that include nitrogen. This one is found it particularly interesting. Triangular ozone cannot exist. It should be stable at very low temperature, but there was one group, who I always forget, it was a group from China, but I cannot remember the names, that something like 10 years ago, they computed that this molecule just cannot exist, even though it's the molecule that makes sense in terms of Lewis. Yeah, so you have oxygen tunneling, you have nitrogen tunneling, a lot of reaction. This is my favorite, which is Ion-Teller distortion with complexes in organic chemistry. But well, we'll see more. All the story started a long time ago, but I cannot find this book that I found a very long time ago as one of the starting points of this. So most of you are chemists, so we are fine. Physicists, this is an organic chemistry book. Don't recommend it. 1959. The people, especially Hammond, it's very, very known in chemistry, extremely known in chemistry. In the first page, the book, I don't care, but in the first page, they show these molecules. And they said these molecules, these strange molecules, have been reported, have been synthesized in later years. These are not molecules easy to synthesize. And they said, all of these have not been prepared yet. A situation subject to change. Yeah. Organic chemistry, the thing that they like most is to synthesize molecules, new strange molecules. So that was the first edition. This is the second edition, which they said we synthesized these molecules since the first edition. And this one, we are trying. Third edition, same. These ones have been synthesized since the previous edition. These ones we are trying. Now, if there are organic chemists here, maybe you can recognize some of them that they do exist. For instance, this the dodecahedrine. Yeah, very expensive, but it was synthesized some time ago. Fourth edition, semi-history, these were synthesized, these were not. Yeah, you might recognize this tetrahedrine with the substituents. That was a big achievement to synthesize that molecule, but without the substituents, still no, nobody could see it. It couldn't be synthesized. Some of these I checked, some of these were apparently synthesized, appear in the literature. I don't know if it was not reproducible, at least not enough to say that they really exist, but they exist. But the question with all this stuff was, are these molecules even synthesizable? Can you prepare them? Maybe they are completely unstable. There's no point in trying to synthesize something that it will break apart in a couple of seconds. So this is the story. Quantum tunneling instability. Let's check the stability of these molecules, not only according to the barrier, because if they have a barrier, it doesn't matter how small that barrier is, there will always be a temperature where the molecule can be stabilized classically. However, if you have quantum tunneling, which in principle doesn't depend on the temperature, then what can we do? We cannot stabilize it. So this is the point. Quantum tunneling stability, or how we like to call it, a QT. And we try to find a good sign that will work as a symbol of the QT. We decided that this one was the best. You see, my artistic skills are fantastic. How we do all these computations, just very, very shortly. We have the profile of energies of the reaction. We can easily calculate the minimum energy pathway. Yeah, we start from the transition state and we fall through the path of a maximum gradient, and we have the reaction coordinate. This is good, this is nice for classical reactions that go through the transition state. However, when you have quantum tunneling, not only the activation energy is important, but also the distance. And sometimes you will need to cut corners, make the distance shorter, so even if the activation energy will be larger, being shorter, you will minimize what is called the action, which is in the end what defines the tunneling. So we have to find what is called the least action pathway. Okay, I'm not doing all this math. There is a program for that using the method called small curvature tunneling, which basically calculates the minimum energy pathway and then takes frequencies all around this curve. So they map the surface surrounding it, and it knows some algorithms, mysterious algorithms that can tell you how to minimize this action. We use Polyrate, it's the program that does all these computations, but connected with Gaussian, which is the program that computes the electronic structure. Okay, most of the reactions we are doing, just for some details, are made with the profile of energy is made with DFT, mostly with MO6-2X. The computations are very slow, very heavy, so we need to do them with DFT, with a relatively small basis set. MO6-2X works perfectly well, not perfectly, well, works well enough for activation energies because it has a lot of Hartree-Fock exchange, exact exchange. And that's very, very important for barriers of main group chemistry. Don't use this for complexes, for instance. We can talk about functionals later on. But this is a good functional for most of these reactions. But it's not perfect, so we improve that with a kind of interpolation. We take some values, activation energies and reaction energies with coupled cluster, and then we improve those results much more. Okay, so this was, I think, my first molecule that I tried to check by this issue of quantum tunneling instability. The group of Gabriel Merino in Mérida, they hypothesized, they designed computationally the molecule that will have the shortest carbon-carbon sigma bond. If you see that distance, it's extremely short for sigma bond. That was a very nice paper, but then came the group of Grunenberg, and they ruined everything. They have a nice method to check the force constant of the bonds, and according to this curve, whatever falls outside of this curve tends to be more reactive. And this molecule here is this molecule here. So they say that the decomposition of this molecule, this opening up of this structure, requires only something around 7 kilocalories per mole, something a bit less than 30 kilojoules per mole. So it should be stable, but only at really low temperatures. For sure, not over liquid nitrogen. So is this molecule synthesizable at all? Okay, so in principle, it is if we are at very low temperature. Now, you know Betteridge's law? It says that any headline that ends in a question mark can be answered by the word no. It works perfectly well in journalism, in all the web pages. Can we lower our cholesterol? The answer will be no. Everywhere, check it. So, is this molecule synthesizable? Nope. We tested it by tunneling. We call this check in the box. Randomly, it will open like a box, right? Yeah, I should get rid of that. But this is what we saw, computational, right? Nobody synthesized this molecule. The blue line here in this Arrhenius plot, it's what would be classically. Always a line. But when you are reaching a plateau like this, where it begins to be non-dependable on the temperature, that's a clear sign of tunneling. And depending on the rate, we can convert it to half-lives, and according to the computations, half-life of 10 microseconds. Imagine synthesizing a molecule that breaks apart in 10 microseconds. Imagine the time you need to go to the NMR running with a tube, trying to find the spectra of the molecule that it's not there anymore. Okay, so maybe it's a philosophical question. Yeah, you can prepare it technically for 10 microseconds, but you will never see. This is the question of if a tree falls in the forest and nobody's there to hear it. Does it make a sound? So if nobody can characterize, detect this molecule by a spectral IR, whatever, does the molecule exist? Okay, this is a clear duty. Now I have some questions for you. Yeah, and I will put points. You have to tell me if these molecules are stable or not. Will these molecules be stable, or will they suffer the quantum tunneling instability? First example. Yeah, you two, you are not allowed to answer. This molecule decomposes by a, I can never remember this, retroasa Diels-Alder cycloreversion. Yeah, it's like a Diels-Alder reaction, but in the opposite way. The thing is that when the electrons move cyclically, they will produce these two fragments. It will fragment alone because the product, especially the nitrogen 2, right, it's extremely stable. Okay, so generally we learn in chemistry reactions that go in the opposite direction, but all these reactions go in the decomposition direction. Okay, so it looks like this. Very nice. It has an activation energy of 37 kilojoules per mole. Who says that this is tunneling? Raise your hand if you think that it is tunneling. Raise your hands if you think that it is not. Raise your hands if you are sleeping. It should be completely stable, like classical reaction, thermal reaction. How long that you want with this barrier. But if you do tunneling, disappears. 3 minutes. The accuracy of my computation is not high level, right? It's an order of magnitude. Really, that's the best that we can achieve. And then the solvent makes a huge difference, and then the temperature obviously can make a huge difference. But if you are 0 Kelvin, more or less it will be there for minutes. Can you synthesize and characterize this molecule? I'm not sure. This is for sure acute. So is this undetectable? Is this unisolable? Is this unsynthesizable? These are valid questions. Let's see this other molecule. Activation energy 107 kilojoules per mole. Is this a QT? What do you think?
Probably.
Without tunneling, never mind. It might be stable even at room temperature. With tunneling, it's actually stable for more or less 1 year. Again, 1 order of magnitude error. Yeah, take that into consideration. So this molecule is actually stable. Yeah, that's my favorite joke. Yeah. Okay. This one, I'm bringing it because, okay, the molecule itself doesn't exist. Nobody saw it. It decomposes exactly as one of the previous ones. Just the nitrogens are set in a different direction. The pericyclic reaction is quite different. Yeah, let's not enter into too much organic chemistry now. Activation energy 29 kilojoules per mole. It should be more or less stable classically. Is it a QT?
Yes.
Yeah, probably. Yeah.
Yes, it is, but much less than the previous one. So is this undetectable, unisolable, unsynthesizable? Undetectable, I won't think so, because if it really one day, you can detect it. Unsynthesizable, probably you can synthesize it and see it. Unisolable, it is. You cannot keep it in your flask. It doesn't matter which temperature. It will go away in a matter of days. So why I'm bringing this particular molecule? Because this molecule appears as a prototypical example of these cheletropic reactions. In several books, there are several books on pericyclic reactions, and this famous book on physical organic chemistry, they bring this molecule as one of the main examples of this family of reactions. But the molecule itself, nobody saw it. Doesn't exist. Nobody synthesized it. Or maybe there was one group, I cannot remember, like 40 years ago, that makes these two reactants which should make this molecule. I don't know how. I have no clue of organic chemistry, but this should give that. Instead, what they saw was that there was some magic, and then they saw these products. So the molecule itself apparently was there, but they could not see it. They had to do the same reaction at very, very low temperature and see very fast if they see some signs of the spectrum of this molecule. Okay, meanwhile, probably it was synthesized, but nobody saw it. This one, stable or not? Yeah. Okay, yeah, we all have 1 point. This is a known molecule. Exists since the time of Kekulev. Yep. This one is known, that one is known, that one is known, that one is known. Depending on the isomers, right? Several possibilities. But that one is unknown, and especially this one, hexacene, is unknown. people cannot stand this vacuum. You know that we have two molecules, how do they call these analogous molecules to benzene that we don't have in our collection. Nobody could synthesize them. I don't know how hard people try to synthesize them, but people really want them. Why? More than an academic issue, why would people want to synthesize them? Because they are very, very exothermic, and they can be used for good or for bad. This unknowable molecule, we will see. So you can do a lot of bad stuff with this one, but you can also do a lot of good stuff with this one. Okay, so this reaction, there was no proper study checking its stability, and we didn't do a proper study as well. So nobody really knows. What we all know is that if this molecule has a barrier, because possibly it's barrierless, it just doesn't have any activation, any transitional state. But if it has a barrier, and we checked with a functional that gives the maximum barrier that we could find out, so to have an upper, what do you call it? Upper
bound.
Upper bound, that's a word, thank you. So this is an upper bound of its stability. If it is stable, if it has a barrier, it will be very small, but anyway, if it's small, you can put it at 0 Kelvin and it will be stable, it should be stable. No, it cannot. It will decompose in picoseconds. Okay, so this molecule is completely impossible. We should stop trying to create these kind of molecules. This one was a bit better, not picoseconds, by microseconds. Yeah, not that doesn't really matter, but it's better. Don't try also with the first thing people try to think of is let's use some, let's change nitrogen with heavier nitrogen, 14, 15. Instead of 20 microseconds, it will be 30 microseconds. And isotopes doesn't change the story. So at this low level undetectable in solvent synthesis, undisputed, undefeated system that cannot exist. We try with some substituents. Here we have a position where we can put some groups. And these more or less can work. And there is another group that computed what will happen if we put some Lewis acids. You see, this is a set of Lewis bases all around. If we put Lewis acids, maybe it can be stabilized. I don't know. Got to check that. This is, maybe we can go to the stars with this. Who knows? Probably not. But anyway, we can, computational chemistry, we can do whatever we want, right? This molecule, it's a QT as well. It will decompose very fast. This molecule was never synthesized. It's actually like the previous molecule. It was used as an intermediate to create cyclobutadiene. So it should exist, but as far as I know, it was never detected. It was never characterized. We tested something else here. We tested putting it with an electric field. So here is the profile of energy of this reaction, of this decomposition. It's actually quite narrow, and the barrier is high enough. Yeah, still a QT. But if we put an electric field and we turn on the electric field, we might do this: higher barrier and wider barrier. Because this molecule has an important dipole moment. But more important than that, the molecule has to have a different dipole moment in the reactant and in the transition state. So maybe we can stabilize by an electric field more the reactant than the transition state, and then we make a bigger barrier. And then we can stabilize actually the molecule. mean, this is easy to think about computationally, where in the computer in Gaussian and just right, field equal x plus 100, and that's it. Yeah, there are some tricks because you have to put it in the right direction. This is not uniform. It has to be in the vector of the dipole moment. It's a bit tricky, but if you can do it in the lab, and that it's not an easy task to do, then might be possible to synthesize and stabilize this molecule by a this is an extremely strong electric field. It's not something that you can find in a shop. And what about toning the polarity, toning it down? Then the barrier will go in the opposite direction. You stabilize more the transition state than the reactant, and then the activation energy will go lower, and then the molecule will be actually much more unstable. Yes, so we call this switch chemistry. Now, we had a Nobel Prize about click chemistry. Well, it's time for switch chemistry. Yeah, because really, it is a matter of turning on a switch. Okay, so we have tons of molecules right now that we computed the stability with pericyclic reaction. That's kind of easy. We know exactly how they will break. So we did a lot of systems. We plotted in a graph we call it a semi-classical quantum tunneling graph. Well, this part here is the quadrant of surprises. So what it means is y-axis is the activation energy. So it gives us a hint, semi-classically, of what will be the stability of the molecule. So up to this line, whatever is up here will be stable in liquid nitrogen conditions, right? 77, 78 Kelvin. But here, in the x-axis, we put the logarithm of the half-life, including tunneling. So at 0 Kelvin, the lowest temperature that you can reach, this will still give you the half-life of the molecules. So if the molecules appear up, but to the left in this quadrant of surprises, they should have been stable, but they will not because of tunneling. So all the systems here are really the cuties, the one that we are supposedly should be stable, but they are not. Okay, the first model of story is that there are many more unknown molecules than known molecules. There was a study, mathematical study, that checked how many combinations between atoms you have that still cover Lewis structures in small structures, in small molecules. I cannot remember how many atoms there were, and they were 10 to the power of 60. There are more possible molecules than atoms in the universe. So obviously we cannot do that. And we are speaking here about small molecules, not proteins, right? Obviously. There are many more unknown molecules than known molecules, but only computational chemistry can state if they will really be stable or not, including quantum tunneling. You cannot test everything. And if a molecule is not stable, how can you prove it experimentally? Can you say, I couldn't synthesize it, so probably it's unstable? That makes no sense. People will tell, you couldn't synthesize it because you're a lousy chemist, right? So the good thing about this is that nobody can test our hypothesis. Because if we say that you shouldn't try to synthesize it, nobody will try to synthesize it. Yeah, so right now we are checking like 1,000, not all of them, well, taking them by group, but there are like 1,000 isomers of benzene, all of them of higher energy, and we're checking which ones of these are stable or not, according to the quantum tunneling stability principle. Second moral of the story, if you cannot synthesize a molecule, blame the tunneling effect. Yep, you have always a way out. Okay, this was exothermic tunneling. What about isothermic tunneling? In this case, it can tunnel back and forth because both wells are in the same energy. right? If the reaction is fast enough, you may see the ostrich in both places, because the reaction will be faster than your equipment. For instance, this was the first one that was the master of all the heavy atom tunneling reactions, cyclobutadiene pi bond shifting. The reaction studied by Carpenter in the early 80s can go from there to there. The pi bonds can switch positions very easily. And then it can come back. And if it does this extremely fast, then this is what you are going to see. It's not that this is the molecule. This is not benzene. There is no resonance. It's really going very fast from one to the other. Extremely fast, and it goes by tunneling, mostly by tunneling. So in this family of pi bond shifting, we studied lots of molecules. Yeah, obviously cyclobutadiene, lots of groups studied this molecule. But cyclopropenylana, anion, pentylene, we are expanding the paper on pentylene. It's under review right now. Ethylene. Have you heard about this allotrope of carbon? New molecule, yeah? They synthesized this molecule, putting atom by atom with I think it was by AFM, if I'm not mistaken. They move atom by atom, they do the reactions on a surface. And they created a new allotrope of carbon, only carbons there. So when we saw that paper, we had to run. We need to publish this now. So we ran and managed to compute the tunneling of this reaction. And you cannot see the triple bonds. The question was, are they all double bonds all around that, like allenes? Or are they triple bonds, single bonds, triple bonds, single bonds? It is like that. But in the surface, things, it will get stuck in one of these structures. But if you have this molecule in gas phase, it will go very fast from one to the other, extremely fast, such as that you will see it as if it was an allene, even if it is not, because of quantum tunneling. Oh, this was a mess. This was a huge paper. This, whatever chemistry you want, you can find it in this molecule. But I'm not going into this molecule right now. This is another family of reactions where we have carbon tunneling, we have oxygen tunneling. We wanted to open the toolbox with other atoms, like boron tunneling. In this case, we call this a ping-pong tunneling. You can guess why. Should move very, very fast by tunneling. Again, you cannot keep the boron put in one side. Similarly, this is a tetraethyl bond of the family of the halogen bonding, if you know what I'm speaking about. The fluoride will ping-pong from one germanium to the other. Depending on what we have here, it will go from seconds of femtoseconds. Now, fluoride is the biggest, heaviest atom that I know can tunnel in a chemical reaction, at least. But do you remember Martin Quack saying that he had chlorine tunneling?
Yes.
Yeah, well, I don't trust him. I have to see that. This one, do we have inorganic chemists here? You're inorganic, okay. Okay, this is not even organometallics. This is purely inorganic. Copper complex with different bonds due to Young-Teller effect. Two bonds are longer, like this, and four bonds are shorter. But who says it has to be like this? It cannot be in this direction, and cannot be in that direction. And who says that it cannot actually move dynamically from one to the other? So we tested that in several complexes, and this movement will be observed in most of them from seconds to microseconds, this movement. It was actually observed experimentally in a solid state, in a matrix, in the 70s, late 70s. They began to see the classical signs of tunneling, but this was late 70s. The heavy atom tunneling was not in the vocabulary. So they couldn't say that this was a sign of tunneling. They couldn't think of it. So we have at least some proof obtained before our experiments that this can go by tunneling. Here we have another example of fluorines tunneling. This is the only molecule that I know that it exists. It was very hard to check if this molecule should be octahedral or not. All the computations say that the molecule is not octahedral. It distorts a C3b system. However, the movement of these fluorines will take microseconds. So it is not a surprise that experimentally they observe some, depending on the experiment, they might observe that the molecule is actually octahedral. Not octahedral, just moving very fast from one to the other. So this is the heaviest atom that we know that it's tunneling, except for Martin quark that I have my doubts. Okay. But here we are reaching the main molecule in this isothermal tunneling that I wanted to show you. This is diamond. Yeah, you recognize that diamond structure? But in the middle, we substituted one carbon with one nitrogen. Now, nitrogen has one more electron, so you will have 3 bonds that will be sigma bonds with 2 electrons, classical sigma bonds, and one of them that will be longer because the extra electron goes to an antibonding orbital. Obviously, if you see this, and after all the things we have been talking in this lecture, you can imagine that what we are looking for is this movement. The long bond might switch from one position to the other. Actually, it has 4 positions. So this would be a quadruple well-degenerate rearrangement with an activation energy of 67 kilojoules per mole. Will this tunnel or not? Well, the answer is someone did the experiment before us. We did the computations to check if the experiment was done correctly. Yeah, never mind. Yeah, the experiment was done correctly, yes. But if our computations show that it can tunnel more or less at the same rate, then it shows that our computations are quite good, right? So it can tunnel, but very, very, very slowly. To test this, we cannot do diamond. It's not with our tools that we do this. We have molecules. So what we did was an extrapolation going from a very small cluster, this one, to making it bigger and bigger and bigger up to something close to a nanodiamond. These are called diamondoids. And this is a proper nanodiamond. And then we can do the extrapolation to diamond. Now, actually, all the properties in terms of reactivity of these 2 molecules and even these 2 molecules are basically the same as in the diamond. So we can do that kind of extrapolation, and we did that. We observed that in diamond, the half-life of this movement will be more or less 1 month. Very slow. The experiment was done in, I think, liquid nitrogen, just higher temperature, so there was something called thermally activated tunneling. We are occupying higher vibrational state because we already are putting some heat there, and from there the tunneling, the barrier is much lower and narrower, the tunneling is much faster. So this is thermally activated tunneling. It can do that. From 0 Kelvin, it's very, very, very slow. But this is for diamond. What about the smaller clusters, the diamondoids? In diamondoids, the bonds are much flexible. So the activation energy is larger, higher, and the movement is wider. So there, the movement will be much slower, and with the diamondoids, it just won't tunnel. It will be too slow. Then we tested oxygen, 1 extra electron, so 2 long bonds, and the energy is more or less the same, but the movement was larger. So if you have oxygen as an impurity in diamond, it won't tunnel. With glass, obviously, it's much, much slower. Last thing we tried was boron. Basically, boron is nitrogen. Instead of 1 electron in an antibonding orbital, it will have only 1 electron in a bonding orbital, so the bond order will be the same. But the activation energies were way lower. So for the smaller clusters, the activation energy was already 15 kilojoules per mole, and the boron can tunnel from one position to the other relatively fast. more or less in the time of one symphony, it will occur. If you have bigger clusters, the reaction should be faster, way faster. It is strange to have boron as an impurity. You have to prepare them. You have to synthesize these diamonds, nanodiamonds with the boron inside as impurities. But if you do that, the tunneling there will be immense, extremely, extremely large. But these are still diamondoids. This is not diamond. If you have bigger structures, especially diamond, the activation energy will actually be negative. So for the smallest diamondoids, you will have an apparent boron delocalization. It will look like the boron is moving. It will look like the boron is everywhere, but it's actually moving extremely fast. But with diamond and nanodiamonds as well, what does it mean? Negative energy? It's an artifact. It's not a reality. It means that the 0-point energy is over the activation energy. And then the system is completely delocalized. This will be a real boron delocalization. The boron will be everywhere. This is a quantum effect. We are seeing the dispersion of the wave function of the boron. This is known with hydrogen, which is much lighter, of course, in some very specific systems. With boron, it's a hypothesis. It's a hypothesis. We cannot be sure without the methodology if this really will occur, but all points to this, that we will have boron completely delocalized, quantum delocalization of the boron in the molecule. Okay, and to finish, we have here our nitrogen into the structure of diamond in one of the positions. I call that the left position, right? The tunneling rate will be extremely slow, exactly as we spoke before. And what if we put the electric field, just as we did before? We did the computations, and when you turn on the electric field, the nitrogen will tunnel to a specific position, depending on the direction of the field, with a much faster half-life. From 1 month, we turn it into a minute. This is a very, very, very strong field. Very hard to achieve this field, but you can make the movement extremely fast compared to the previous one. This because the barrier now is lower and narrower. And then, if we turn off the field, the nitrogen will get stuck there. It won't turn into the previous position because it takes 1 month to turn back. And then if we heat the system a bit, then by thermally activated tunneling, the nitrogen will rearrange, will scramble to any of the 4 positions randomly. So we have a way, theoretical way, very hypothetical, as I said in the conference. This is science fiction. This is not science. But technically, you put a field, you put the atom in the position that you want. You take out the field, the atom is there. It keeps the information. You heat it up, and you can delete the information. This can work, may work, might work, maybe in a couple of centuries, as an atomic memory device. 1 atom keeping information. And this is the work of physicists to try to create this, and for engineering to put a field that will work. Not my problem, okay? Technically, we have first the first idea of this, yeah? So this is a very cute idea. It won't work, obviously, but it's a very nice idea. So let's just summarize this. Lots of cases of heavy atom tunneling. We saw that ostriches can fly. So there are many systems that have the problem of quantum tunneling instability, which they will be undetectable, insoluble, unsynthesizable, depends on the system. We saw what happens with an electric field and the switch chemistry. Lots and lots of isothermic tunneling reactions. this is by far my favorite. We saw that nitrogen can tunnel into diamonds and that you can manage that according to an electric field. I think that's good enough for today. Okay, thank you.
Thank you, Sebastian, for I think a very nice talk. Any questions from the audience? Yes.
Can I ask two?
Sure, yeah.
First one is, can you visualize really the reaction coordinate through which you tunnel and draw maybe a potential? These are very complicated multidimensional problems. Have you?
Yeah, no, not with the methodology that we have, is small curvature tunneling in polyrate. I checked and we cannot. However, there are other methodologies, especially instanton, if you heard about it, that actually do that. I check, but not my field exactly. I'm not working with the instanton theory, but they can show you what would be the path of least action.
And do you know any cases where you also affect particle exchange of the two atoms, and therefore exchange effects might be important to take into account?
Well,
because I didn't see any cases there. I mean, there was one atom moving across two wells, I guess, like the xenon fluoride. But you could think of the two atoms a bit like what a methyl rotor will do along the 3V axis, and therefore, you've got then the quantum statistics kicking in.
It's a debate. You see, when you have isothermal tunneling, it has to be isothermal tunneling, and the reactions are very, very fast. You can think of a coherence between the two wells. Yeah, this is something physics that I just beginning to learn, right? For instance, the ammonia inversion is the most famous example. When you have coherence, you have a splitting of the levels. And if you have splitting, means that you have one set will be a superposition of those states, a plus superposition, a positive superposition, and the other set will be a negative superposition. Now that will work as stationary states where the system is in both wells at the same time. For that, it has to be a really fast reaction, which can happen. Some of these examples were extremely fast. And then they have to be purely gas phase without any interactions with anything else, because then they will probably decohere.
I can tell you that in solids is well known methyl rotors tunnel, and in a coherent manner, meaning the best way to know this experimentally is to see that you've got a well-defined excitation which is well below the vibrations, and that tells you that it has to be tunneling. And if you do, if you do the barriers and calculate the barriers and you relate them to the moment of inertia, that's what you get. And this is in a solid. So if you're at low enough temperatures, say below 10 Kelvin, coherence will not kill you. And you've got a qubit there, in reality. Because
yes, I guess so.
With spin 3/2, which are coherently tunneling.
Well, technically, you can also do the, well, no, it's a bit slower with these complexes that do the movement, but no, that was too slow for that. But I guess, yes, if the reaction is extremely fast, it has to be really fast. With heavy atom tunneling, it's harder, way harder. With hydrogen, it is not, yes.
Thank you.
Yeah, I have a question from experimental point of view. In your first examples, when you remove nitrogen, in your Q2I first examples, what's happening if there are a strong nitrogen atmosphere in the medium? Probably the equilibrium more, the molecule more stable, or?
No, we are speaking about huge exothermicities.
Okay.
The pressure, the nitrogen pressure to go to the reactant has to be millions of atmospheres of nitrogen. I don't know, probably no.
Okay. Yeah. Yes.
Yeah, I have a quick question about the switch chemistry. So in order to make the lifespan of the molecules last longer, you said you can apply this electric field And this electric field is either gonna make the barrier higher, or it also can make, it can either stabilize the transition state or stabilize the reactant. And you can control that to make the barrier either higher or lower. What I don't understand, and that depends on the
Dipole moment.
of the reactor or transition state. What I don't understand is how can this change the width of the barrier? Because as you said from the start, the width is the thing that matters the most, so we can tell if something can happen or not.
Okay. Can I write there?
Yes, I guess.
I think I saw one marker here. Hopefully it will be possible to delete, to remove this. If not, it's his fault. Yeah.
All right.
So, it's very nice. This is one reaction.
Yeah.
Now what we are doing is lowering the transition state, but it will also lower the product.
Yeah.
So this is it. Actually, everything is going down.
Yeah.
Yeah, it's just that the transition state will go down more than the reactant, and we are taking the reactant as the reference.
Yeah.
So when you are building the plot of this, it will have to go like this. So if you see the barrier is lower and narrower. One thing that it's very important, have you heard about the Hammond's principle?
Yeah.
Yeah. It says that the lower the exothermicity of a reaction in the same family of reactions, the transition state will be earlier.
Yeah.
Closer to the higher of the two states.
Yeah.
Earlier means also from an energy point of view, it will get lower. So if the transition state, this graph actually is not correct because the transition state will have to be earlier here. But the corollary that it doesn't matter in classical chemistry, but in tunneling, yes, is that it doesn't make the energy, the barrier lower, but also narrower. It's a trend, it's a rule, not a law. Because in different reaction, it can work completely different. But in the same family of reaction, and this putting a field makes the same reaction, but slightly different, changing the exothermicity will change the activation energy, but also the position of the transition state. And since tunneling goes in this plane, doesn't need to go there, just goes up to here and then it falls, then the barrier will have to be necessarily narrow. Again, this is a rule, depends on how much you are changing the system when you are doing some perturbation. But in this case, classical Hammond.
So actually, I have a question related to the isothermic reaction. So when you have the reactant product of the same energy, you have a reactant tunneling through across the barrier, reactant product. If the tunneling rate is very fast, it's as if the thing is in the middle, right? Can I think of it that way?
Again, no, I couldn't.
So the isothermic reaction,
Yes.
when the tunneling is very fast,
Yes.
let's say a proton transfer or carbon transfer, when it's very fast, can I think of it as that on average, it's in the middle?
On average, yes. However, I'm not sure. Let's say you do an XRD.
Yeah.
My guess, because I'm not fully sure, my guess is that what you will observe is that the system, the atoms, are distributed in the whole section, more in the middle. You see, when you do an XRD, usually you see these balls of something like this, right?
Yeah.
They show.
Yeah.
Or they show.
Divine water factor.
How it is called?
This is the mean square displacement.
Yeah. Okay, which shows something like 50% of the
Like an
possibility.
ellipsoid.
Yeah. If you have an ellipsoid, it means that there is an uncertainty in that direction, right?
Yes.
of the position.
Mhm.
My guess is this is what you will observe, but I'm not fully sure.
Okay.
That has a lot of other things in there, thermal effects.
No, of
Yeah.
course, but
It's not just a clean volume. It's far more complicated than that.
so I think you will obtain something like this in an XRD, right?
Mhm.
That it will be extremely elongated because of the two positions that you will have. But I'm not sure. I guess it depends on the way that you
Yeah, also on the Young-Taylor distorted system, you describe one direction, the bound length is in one direction, and you can tunnel to the other direction, which is lengthened. So if you do an experiment, let's say measure the XRD, you get the distance. I don't know if you should get the average non-Young-Taylor distorted structure, or do you really get a distorted structure? Because if you get a distorted structure, it should be in one way, not in the other way, right? So
no, you should see that it's distorted in the three directions.
I think maybe the best analogy, I think I know what you mean because we have this discussion often.
yeah,
Depending on how you do the experiment, you could think of the two wells as being two mountains. And imagine you lived every day of the week, each day you lived in one of the houses. If you take the average of the where you are, you're always living in the valley. And that's the wrong place. You never live in the valley, you live in the houses. So depending on how you do the ensemble average,
mhm,
and what you put into the model when you do, because XRD has a phase problem, meaning you don't have a direct reconstruction of the real space arrangement of atoms. Depending on what you put into the model, you might get very different answers.
Okay.
Because at the end, it's a model that you put through a computer to be able to match, to do a refinement of your data.
mhm.
So if you put two sites, you're going to get an answer. If you only put one site, you might get living in the river every day of the week, although your houses are in the mountains. So
Yeah.
very much depends on how you play the game.
I guess so.
Yeah.
In these particular cases of the Young-Taylor effect in the complexes, they did the experiments with EPR. So
Uh-huh.
that gives you completely different information in any case. Yeah, they just saw the rate of the reaction that was going to a plateau.
Okay. All right, thank you. Any more questions? For now, let's thank the speaker. Yeah, okay, to check, but there's no questions from the online audience.
Nos vemos con el bueno. Después arreglamos bien.
Sí, por mail, ya, no te preocupes.
Yo me presento. Yo soy el responsable.